So running the JVM and running it fast means that you want to translate the bytecode into machine code. Now this is not new, it's been done several times before, and in the 90s the first compiler that compiled bytecode into machine code was ExactVM, followed by the Java backend that was developed by the compiler team at Sun, followed by C2 that was acquired from a small company that made a virtual machine for Smalltalk, and C2 is the one that you most commonly hear about in Hotspot nowadays. And after C2 was acquired, someone developed a new, more standard compiler called C1. So C1 came after C2. And then you had other teams at Sun who developed smaller JVMs with smaller compilers, still very good compilers, Monty, CVM. And then you have the research teams that tried to develop JVM compilers that were written in Java, and Maxine is one. The JAX RVM is another one. And then we have Graal, which is a continuation of Maxine. And then you have JRockit, which was a Swedish company, which evolved into this group that's actually here that's been working on JRockit and OpenJDK. And we have J9, which is IBM's JVM. So it's a pretty well-researched subject. Now, what you start, what you do, the first thing you do. Well, the Java bytecode is a stack machine. And it has its origin in P-code from the 70s, so it's not particularly new either. And all our CPUs are register machines. So for performance, we want to go from stack to registers really quick. And how many of you have ever read the Java specification to know how the Java stack frames look like? Excellent. Okay, so the Java specification specifies a stack frame that could be allocated on the heap if you want to, but everyone who wants to run fast usually makes it so that it runs on the stack that's supported by the hardware on the platform. But from a specification point of view, when you enter a Java function, you have slots that corresponds to this pointer, the first argument, the second argument, and then you have local variables coming after. And then in the compiled Java bytecode, it is specified the size of the operand stack. Now this is useful because you can verify the bytecode in advance. Because of this specification, the JVM can control that there are no buffer overruns, there are no breaking types, etc. You cannot mess with operand stack in a way that will break the execution. But it's still just an abstract specification. And if we would like to execute this bytecode, load 1, load 2, add, return, and the argument to this function is 42 and 14. What you would see in interpreter is that, okay, you load the first argument, which is 42, load the second argument, replace it with 56, and you return. Now, how do you translate that into machine code? Well, the first thing that happens is once you translate the bytecode into some sort of intermediate representation. And you do that by going through the bytecode, but not using actual values, but references instead. So we start with load again, but instead of the actual value, 42, we say we push the variable 1. And then we push the variable 2. And then we add. And when we go through the bytecode, we reach add, and then we have enough information to generate something in our intermediate representation that represents adding of 2 registers and storing it into a 3rd register. Now, these are not registers yet, but they are abstract variables. They will become registers probably. Unfortunately, they might also end up on the real stack if you run out of registers. And eventually get the return. So now we have a representation of we have essentially recreated this from the bytecode and get back. A normal compiler, like GCC or something like that, they go directly from the source code into this representation. But we take this slight turn around through the bytecode first. So how do you store this representation in the JVM? Well, there are two obvious ways. Either you store this representation symbolically, which means that you have a data structure that says essentially the string, but in a more fancy way, like you have a struct with bit-packed bits, so you don't waste any space. But essentially, it's just string manipulations. Or you go the other way. And unfortunately, it's quite common to go the other way, because what you're recreating is this tree structure, and everyone who creates trees likes to create pointers instead, and just create pointers to objects. So you could create a tree of objects with pointers. So two major ways of representing the source code. And the question now is, what are the advantages and disadvantages when you try to compile this efficiently and fast into machine code? So clearly, symbolic representation is probably more space efficient. If you're running on a 64-bit platform, every pointer is 64-bit, C++ objects, etc., etc. So in JRockit, we used 128 bytes for an opcode. And the reason why we have a fixed size is because you could do a memory allocator that was very fast and just on these 128-byte boundaries, actually never throw away an allocated opcode, just ignore it, and then when the compilation is done, throw away everything. And you can pack the bits inside the struct. So on a 64-bit platform, usually you don't need more than 4,000 variables. So you only need to allocate 12 bits. But on a 64-bit object pointer structure, you would need 64-bit pointer for each variable. So to reiterate, object pointer representation is less space efficient. So you use 64-bit pointers if you have full virtual C++ objects with headers, etc., etc. So the question that everyone asks themselves right now is symbolic representation slower? Because you think, well, if I have all the pointers created already, clearly it must be faster to just walk the pointers to find the source. Well, not necessarily, because when you get the larger set of pointers, will it fit into the CPU hardware cache? Will you get sort of memory fragmentation? And this ties into the major problem that the JVM JIT actually wants to solve. The JIT wants to get rid of memory accesses that are not reliable on the same location. Because if you just sprinkle memory accesses all over the memory, you get cache misses. And cache misses in modern CPU hardware is very expensive. So assume that you get a cache miss. How many cycles can you spend, or how many CPU instructions can you spend to avoid that expensive cache miss? Well, depends on the situation, but everything between 100 and 1,000 CPU instructions. So if you can recreate the value from a huge table that's very large in less than 100 instructions, do that instead of reading from memory. So, but everything depends on how often you reread the memory, how large a cache size is in your CPU, etc., etc. But everything is about memory access. So in this case, the compiler examines the multiplication. The compiler wants to find the source for V7. What operation created the variable V7? And by examining that source, it can check, okay, do we have a guarantee that it's less than 16 bits, which means that we could use a smaller multiply instruction or something like that. So in a symbolic representation, won't we have to scan for all places where V7 is created? No, because it's only created in one place. And why is that? Well, it's because when you compile something, you move quite quickly into SSA form, which is single static assignment form. And that's something quite interesting, because when I said variable here, it's actually constant. And where did this SSA form come from? It's well known that the SSA came from IBM quite a lot of years ago. And I think it appeared because it sort of automatically appears when you create an object pointer representation of the source code, because it's always nice to reuse a pointer to this source. So by the construction of that object pointer structure, you almost get a single static assignment, which means that you follow the pointer, you get to the source. You don't have a chain of assignments on the way that you can have in a symbolic representation. But it's easy enough to maintain a SSA form in a symbolic representation. You just have to be a little bit careful. So to look up where the source is for symbolic representation, we can store the source opcode index in the metadata. So a single lookup in the variable table, which is so small that it's cached in the CPU, can add a barely noticeable indirection to actually find where the variable came from. There are many other examples, but this is a simple one. The other reasons that's interesting when you compare symbolic representation and object and pointer. Symbolic representation can be rewritten in place. So we have a representation of an add instruction. To go downwards to a more platform-specific representation, we just rewrite the symbolic information, which is usually you write a number into a few bits. But if you have object and pointers, perhaps you can rewrite an object, C++ object. You could replace a virtual table pointer, or you could construct objects that can change type or something. But most people just allocate a new C++ object with the correct opcode type. Yeah, so I already said this. Something that can be done in a symbolic but not in object's pointer is register allocation. And why is that? Because register allocation is when you leave single static assignment form. You really can't use the same source because you have a limited number of registers. You will reuse stuff, you will write multiple times to the same register. So you have to leave single static assignment form. And if you are in a symbolic representation, you can just rewrite the symbolic representation. But if you are in an object pointer structure that's sort of inherently SSA form, then there is no space for it. So you have to allocate more space again to store where things that looks very source up here is used here and here, but you can't use the same register all the way. You have to shuffle them around. Yep. So let's go to the code, and soon you will understand what this introduction was about. So take a look at this simple code. If x larger than y, do and multiply with 2, return x plus y. So JRockit contained a single compiler, but it could work in two different modes. One mode was to get this machine code out as quickly as possible, because JRockit did not have an interpreter. So JRockit truly compiled every single bytecode into machine code before it even executed anything. But if you start Eclipse or something with JRockit, you can't see the difference because it generates machine code so quickly to get it up and running that at that time we didn't need an interpreter. That's a fast compiler. But on the other hand, JavaScript compilers today are very fast, and they're moving from JavaScript source code to machine code in the same speed. So it's possible. So what we have here are the DIT version. And I'm not sure if you can see it. When I clicked here, I can see the different stages of compilation. It's bytecode to high level to medium level to low level, and fixed floats is actually register allocation and emit code. So we can see that in this demonstration, we skipped the process of going from stack-based to abstract variables because it's so fast. So we just directly see that it's a compare between the variable 1 and variable 2, and then either you do the add direct or you do a jump in between. Can everyone see all the details? raise your hand who can't see? Okay. Indeed. Okay. So in the JIT, I'll just skip ahead because nothing happens here. We move to machine code very quickly, so we don't do much at all. We just introduce. This is a trap. It's meant to capture the thread when you want to do a garbage collect. So when you want to do a garbage collect, you suddenly read protect that page, and then all the threads stop. You do the compare, and you have the same code. Essentially, you can see in JRockit we could move from abstract variables into partially register allocated opcodes, because some opcodes have a desire that, okay, you have to store things in array X because we always return the values in array X. Then it adds the frame entry and frame exit. And this is almost the final machine code. It's not rearranged, but everything is there. Okay. Nothing strange, simple. In the opt case, it does quite a lot more, but doesn't, in this simple case, the result will be the same. But you can see the different steps here. We enter single static assignment form, and we do also stuff that actually doesn't help us much because the code is so simple. But we can jump here. Oops. And what you can see as an interest here, single static assignment form, when you control flows merge, then you have to tell the compiler that, okay, these two variables will join and become this third variable. And you do that with fee nodes, or as it's called here, join nodes. Essentially, these two come in and they will end up in these abstract variables. The join nodes is essentially just a hint to the register allocator. You know, it would be very nice if you could store all these three abstract variables in the same register. Because then you don't have to do anything. When you merge from these two control flows, you will always have the source in the same register and the output in the same register, so there's nothing left to do. And then we move on. Let's see. Yeah, somewhere here it performed the register allocation, and we now have all the finished registers. So you can see it also replaced the multiplication with 2 with an addition. That's nice, I suppose. I don't think it really matters that much on the latest hardware, but looks good. Okay, so now you've seen what it looks like in JRockit that uses symbolic representation of a compilation. Now we're going to have a look at what it looks like in Hotspot. Okay, so Hotspot. Pardon? Yes. So why does it look like this even before we have parsed, well, when we have parsed just the first bytecode? Well, the first thing to note is that the C2, the name actually comes from a phrase called sea of nodes. There will be a lot of them, so it should be called ocean of nodes. It actually integrates the conversion from bytecode to an intermediate representation as part of the compilation process. So it doesn't do this very, very fast BC to high level conversion first. It actually builds the entire ocean of nodes at the same time while it's compiling. It's okay, this was a research project that accidentally got stuck into a production product. And you can see it starts out with all sorts of interesting nodes here. In particular, you see these merge mem nodes all the time. And essentially, a way of hotspot C2 to try to track writes to memory in such a way that it knows when memory might be invalid and sometimes, and it can use that for global ordering of the machine code at the end. Whether this actually makes any difference. Can you hear me? Yep. Whether this actually makes any difference to the resulting code is a subject of discussion. But it's sort of cool, but it takes a lot of space. So let's move on. We load the bytecode successively here, and we can see how the graph gets bigger and bigger. Now it looks like that. Okay, we go here. Now it looks like that. Yeah. You remember this is what we're compiling. Okay. So then it starts cleaning things up. Okay, it realized that, okay, maybe I didn't need to allocate all this stuff. So this looks much better. And we can see that, as I said on an earlier slide, it keeps less of the bytecode ordering inside this graph on purpose. In fact, you could say that C2 purposefully avoids remember the order of the bytecode, because it creates calculations like these that are only the trees of the dependencies. So you have a sorted tree dependency of the execution order, and you have not sorted, but it's by the arrows. And you have a data dependency with all the data dependencies intermingled in the same graph, using the same pointers, using the same slots. So you don't know which slot is a control flow pointer, you don't know which control slot is a data source pointer, whatever. Also, every single of these arrows are in fact double pointing arrows. So each of these lines require two 64-bit pointers. Okay. So the idea here is that, okay, when you want to generate the machine code in the end, you sort of start with return and they just pull like a lazy pull system of streams, and you get the machine code out. Now, as I said before, when you go to the final code, it's replaced all the nodes. So now all the old ones are thrown away, and you created a lot of new nodes to represent the machine code. Now, the resulting machine code is just the same as the JRockit, just took a little bit longer time to get there. Okay. That's a very simple Java function. Number 2. Profile says do not inline. This means that what can the compiler do when you see that no one has never ever called test1? And you can't know this, of course, but in my test case, I've set up so when I'm running test2, x is always equal to y. So profiling information will tell both JRockit and Hotspot that test1 has never been executed. So let's take a look at JRockit. So nothing is happening, which is why we can jump ahead. So this is not particularly instructive but you can see that it's marked the call no inline. And it did so because no one has ever called test1 in this run. So we don't want to inline it. So we get down, and in the final code it looks like this. The call is still there. Simple, trivial. And if we look at Hotspot, it does the same thing. We jump here. You can see that it maintains a call static Java here. Okay. Profile says inline. Same thing. And we can jump directly to inlined. So here you can see that it deleted this call. That's why it's dashed. And replaced it with these green blocks, which is the test1 source code, the test1 bytecode. It tidied up a little bit. And here it performed a strength reduction, which is where it discovered that you're multiplying with a constant 2. Well, we like to replace that with an addition. This is interesting as well. Copy prop happens all the time in JRockit because it uses a symbolic representation, so it's quite easy to slot in new stuff and just move these abstract variables from an abstract variables to an abstract variables. The moves are just abstract representations that you link this chain of assignments together. In hotspot C2, everything is a single pointer to all the way. So in hotspot C2, you never see copy prop in that way. It's an artifact of how symbolic representation works. Again, you can ask yourself, is it slower to maintain these chains and then clean them up in a copy prop compared to always maintaining a correct pointer? Who knows? Perhaps it's more efficient to do a lot of batch changes and then after a while clean everything up than to maintain everything at the same step. I don't know. It doesn't seem to cost much for JRockit anyway. We get more copy prop, compact blocks, okay. Now it looks almost as it's going to be in the end. We can go here, Deadcode. Yeah, there were some stale move operations here that was never used, and the reason is if you look at V3, there is no one using V3, so you just delete it. But if you click on V1, you can see everyone is using V1. And then we get to the final code, and it's exactly the code that you would expect from a proper inlining. Okay, take a look at this one. I'm closing all these tabs. So okay, so it's C2 has 2 levels of inlining. It first performs inlining on a bytecode level, where if it can see at parse time when it loads a bytecode that, okay, I can inline bytecode here, it will do so even before handing the bytecode over to C2. Now this is a major problem because when you're at the bytecode level, you might not have done all the nice optimizations that you can do later on to see when the type of something is known so that you can inline, etc. Which is why they added a second level of inlining just a few years ago, which is called incremental inline, which is exactly what JRockit has had all the time. That you can, during the compilation process, you discover, okay, this, I know the type of this variable. Exactly. So any virtual call on this type is not a virtual call because I know where I'm going. And sometimes it's not, you know both the type and where it was created, so you can inline based on things like that. So here you can see that it inlined test1. Okie dokie. Now, remove allocations. Let's see here. Yep. Now, as I told you, I'm feeding this with x equals y all the time, so this code will always execute. It will allocate a lot of objects. The objects are very simple. what will it look like? Well, we can actually look at the JIT first. The JIT code performs a call to initialize a class, allocate the P class, run the constructor on P, and then store A, store B, and then call sum. And you can see from the JIT's perspective, sum is virtual. These are fixed. And the resulting code looks exactly like that, but in machine code. And what it does is that it calls allocator, so everything is just machine code standard. Nothing is inlined. Now, the optimizer. Let's go to virtual to fixed. Here the optimizer checked that, okay, we only have one implementation of sum. So I don't need to make this virtual because I can see the entire state of the bytecode loaded and there is only one sum. So this is not virtual. And then it inlined sum. This call was replaced with the actual contents of sum, which is an addition, and two loads and an addition. And then it cleans up a little bit, but we still have the stores. We have an allocation, stores, a type check or a null check. We have the addition, so we stores. Sorry, if you can't see, you have to shout. Allocate the object, store into the fields, check that the object is not null. Load from the fields, add and return. So next comes one of the most important optimizations in JRockit ever. And it's called clean mem access. And what it does is that it can see that you stored V1 into slot A of P here. So loading from slot A is unnecessary. Why is that? It's because the slot and P is not volatile. So according to the Java virtual machine memory specification, you can sort of assume when you generate the machine code that the system is behaving as if it was a single-threaded CPU running just your code at this particular moment. So if you're single-threaded, you're running, then clearly no one will have time to go in and change the contents of A between this store and this load. And the only way to make the Java machine behave as this was not the case is to mark such a field as volatile. If it's known as to be volatile, then clearly you always need to load it from memory. Otherwise, if you just wrote something to memory, you can just pretend that it's still there. That's fine. And that's called clean memory access. And it's very powerful. We got rid of the loads, and we just reused this known value. Some cleaning. And of course, how could this ever be null? No, it can't. We remove this null check. And then the companion optimization to clean mem access is localize object. Now, localize object is quite a complex optimization because it has to figure out that the object v5 does not escape. And escape analysis is reasonably expensive, but it's very valuable when you use it in the right place. So storing into an object and never using the values means that you can just, I don't care to store there. I won't. And you can see it's pushed along the v1 values into the add function. And of course, the companion optimization here is that, okay, why allocate in the first place? So the final machine code looks like this. That's nice. It's going to be even better later. Now, okay, let's take a look at C2. And of course, it's such a complex program that it takes a lot of data storage to do this. But it actually managed to clean it down quite a bit. Well, okay, sorry. Here it performs incremental inline, and we got all sorts. Let's see if I can find it. Yeah, so here are the additions, etc. Let's go to the end. Yeah, so we in the machine code we got these additions here, one addition here and one addition here. So it managed to do the same thing as JRockit. Okay. Old code, cold code. Now we're never executing this code. And in JRockit, we can see that there are no inlines here. Because when we get to, well, virtual to fixed, and then clean up, remove checks. Yeah, so essentially here we are, and it's not going to get any better. The only thing that remains is the add. This code remains in JRockit, but it's not optimized because it will not inline the calls because they were very cold, never executed. So what's interesting here is that C2 performs is slightly different, which is both its benefit and its bane. And there is only a single call static Java here. Why is that? Here we had 1 call, 2 call, 3 calls. Anyone who can hazard a guess? So where did the other calls go? Well, what the hotspot is doing here is that, okay, this is a cold path. I don't even want to compile this, but I have the opportunity to jump back into the interpreter. So it's called an uncommon trap. And it means that whenever C2 thinks that this, or sees it has profile information, tells it that this execution path is completely not used, then it will just jump into the interpreter. And if you never execute that code, the jump into the interpreter will essentially never be used. But of course, it's not always the guarantee that the variables will be the same. That sounds pretty nice, doesn't it? Because it's an even cheaper way to get around this problem. You don't need to compile that part of the code. Until you study what C2 does, and it turns out that the uncommon trap is actually quite common. And the reason is that many if statements in many places, the analysis currently in C2 says that, okay, this looks like a little bit too much bytecode. And considering the space requirements for C2, I'll prefer not to compile it, so I'll jump into the interpreter. Or it says, okay, it can add guards. Okay, this variable always seems to be 4711 when I'm invoked. So I'll just add a guard here, check that the variable is 4711. If it's not, then I jump to interpreter. But as long as it is 4711, then I can use my nice machine code. So that's like a magic fairy dust that's sprinkled all over the code in C2. And why is it a problem? Well, it's it gets problematic when you have multiple paths and you want to do some heavy stuff optimization on this path, but on this path it's an interpreter. And when it's an interpreter, it's escaping. So I said that you could use escape analysis to discover that the allocation of P was unnecessary and storage into P was unnecessary, etc. If for some reason P is used in a slow path, and you could optimize it away if you had optimized both paths. Well, you can't if you have sprinkled common, uncommon traps all over the place, because everything is escaping all the time. So, and that's also a problem if you have heard of trace-based JITs that actually just take exactly the instructions that you have executed, run them through, and try to make an efficient piece of code of that. And whenever some assumption fails, it jumps out into the compiler. And it jumps out into the interpreter. And this means that a lot of optimization you can't do. But JRockit did not have an interpreter, so JRockit could always optimize both paths, etc., etc. Okay. Okay, so now a more complex example. Here's a coordinate. A coordinate is a 2-element vector, and you can calculate the distance with a square root. Here's a matrix, and it's a 2 by 2 element matrix. You can create a matrix scalar, you can create a matrix multiplication, and you can do a coordinate multiplication as well. There's a lot of objects. Now, this is an expression that I want to calculate. And if we replace it with the Java source code, it looks like this. So it creates a scalar. This function creates a 2 by 2 matrix with 33 in these two positions, because that's going, when multiplied with this, will scale these. Multiplied by a fixed value 2. Multiplied by a new coordinate, kk, which is the input. And multiply and calculate the distance to this coordinate. Yep. Okay? So now there are slightly more steps in JRockit. First, it performs all the inlining. And the reason is, of course, that it can almost immediately see from the source code that everything is static on matrix, easy to inline. So so we'll go here, compact blocks. We can see that the value 33 here is stored into V17, which is shuffled around a little bit, but eventually it's stored into the matrix A, B, C, D. No fancy indexes or tables here, it's just 4 variables. Okay. And we have all the other inlining done. So essentially this is just everything. It's still allocating everything, it's still storing everything. It's loading from these values. It's performing multiplications, additions, etc., etc. It has not inlined this one yet. So let's go down to my favorite, clean memory access. So it's not storing into the matrix anymore. It doesn't store 0 here. Why is that? Is it because it performed a repeated const propagation? So this value here 0 was propagated not only into the store, but also into other values that use it. So, no. So in this case, these, when the scalar is used and multiplied, it's never multiplying with those variables. That's why it's not using these anymore. So clean memory access stopped storing 0 into the matrix. And then we go to scroll down. We can see the loads. It stops loading from the matrix. It just reuses the data. And we get to, removes the nulls, dead assignment removal. We still have the allocation, but we never use the allocated values. So here, all the allocations disappeared. And we can jump directly to the emitted code. So this is emitted machine code. That was slightly unexpected, I hope. Now, C2 can do the same thing. And I won't go through everything, but I just jump to the end. So the merge mem nodes are still here, but they are not used when generating the machine code. So the generated machine code actually becomes the same. So this is a machine code for JRockit, and this is machine code generated by hotspot C2. Okay, so finally boxing removal. Two calls. And it's clean memory access. That's the trick. We can see that it's boxing, but we don't need to actually read from the box because it's like loading from a locally stored variable into that object. And then we get rid of the boxes. So this code in JRockit just becomes an integer addition. Unfortunately, in C2, it doesn't. So in C2, it looks like this, the final code. And clearly, it should be able to do that boxing stuff. Why doesn't it? Well, people have not added boxing support to C2, which is strange. But I think the reason for this is because the C2 source is extremely difficult to work with. So, and as you can see, the graphs are not that easy to follow. So a quick comparison, because one argument would be that C2, okay, it makes a lot of graphs, it makes a lot of space, it takes a little bit more time, but how does it fare compared to JRockit? Remember, JRockit development stopped 3 or 4 years ago. It's still available for download if you want to try it, but it runs only JDK 6 bytecode. So I'm testing JRockit vis-a-vis the latest JDK 8. And I'm comparing it with Graal. And for those who haven't heard about Graal, it's a sort of re-implementation, but more a new mode of development of C2 rewritten in Java. So if you didn't think it took too much space before, it surely takes a little bit more space now. So then I needed a test, and I picked just Apache Derby database, because I could recompile that for JDK 6. We will skip how I set up the test here. And these are the basic tests. And they are more or less micro-benchmarked. So you get very fluctuating results depending on how the micro-benchmark fits with your compiler. So these are, the blue is JRockit with optimizer, red is JRockit with only the very, very, very fast JIT. That doesn't optimize at all. JDK8 server. JDK8 server where you have enabled tiered compilation, which means that it runs the C1 compiler first, profiles everything again, profiles a little bit more, and then runs C2. And then we have Graal. And you can see here, suddenly, JRockit was fastest. Here and here, JDK8 was fastest. Yeah, fluctuates, but it's micro benchmark, so it doesn't tell us much. The only thing that we know is Graal is lowest. Now, here are the other tests in the test suite, and they are slightly more complex. So this test actually creates an account, sets up a user registering in the database, and this one actually performs a bunch of auction system style stuff. Okay, so here suddenly the tiered compiler is better, but in this case suddenly JRockit is much better, but it's not even due to our compiler. So anything goes. So for those who notice that it starts with 2 here, where is BTCJ21? Well, it's here because the scale was so broken, so I couldn't put it into the other graph. But here, for some reason, JRockit performs many, many times faster than the other JVMs. So from performance-wise, JRockit, despite using symbolic, etc., representation of the compiler, definitely gives the JDK8 a match, even though no one has developed JRockit for the last 3 years. What's interesting then is to look at an actual compilation of one of the more important functions inside the Apache Darby database. And SQL parser token manager getNext token seems to be used quite a lot because it's parsing the SQL code. And we can see that the JRockit JIT optimized this, or not optimized it, compile it into machine code in 1 millisecond. It took 500 kilobytes of RAM to do it, and the generated code was 2 kilobytes. JRockit opt took 230 milliseconds to compile it, and the result in bytecode was 6 kilobytes. JDK C2 took almost 10,000 milliseconds. And I'm not quite sure about this number, but around that level, and the generated machine code was 11 kilobytes. So you can see here that all optimizations were running. The spent time in optimizer was 8 seconds, vis-a-vis 57 seconds. So C2 is approximately 10,000 times slower than JRockit JIT. And if you remember, in this graph here, the JIT is fine sometimes. And so you shouldn't over-optimize either, because you already also have the garbage collector, the runtime system, a lot of other stuff that affects the performance. So in this case, the heavily optimized code, which is not so heavily optimized, didn't matter at all. But it might have mattered in this case, who knows? So what we really should compare is that C2 is 40 times slower, only 40 times slower, than JRockit optimization. And there is no particular difference in performance. There are always micro benchmarks that will show you this one is enormously much better on this particular benchmark, or no, JRockit is this much better on this micro benchmark. But in the end, most code looks like this getNext token code, which is really boring. It's just a switch statement invoking a lot of state machines that checks the incoming tokens, parsing. It's not fun at all, just boring. And you can't do much fun optimizations on it either. So, to end my talk, now you have seen what it looks like. how fast it can be when you go from Java code to machine code. And I don't know how many of you knew that you could get so close to machine code as you can. So what will happen in the future with the JVM? Well, unfortunately, C2 is not going away soon. So because it's so slow, they can't use it in different situations, in particular for tiered. So they still maintain a completely different source code base in the same JVM. That's C1. I haven't talked about C1 today, but essentially it's a more standard application of compiler technology, similar to JRockit, but it uses object and pointer storage instead of symbolic representation. Also, it doesn't do many optimizations at all. But it's faster than C2. That's its major benefit. It's still not as fast as JRockit. C2 will stay because they don't have a replacement. People are working on Graal, which is a rewritten C2 with improved source code, but that code is written in Java. And if you just run the Java compiler inside the JVM, you have to compile the compiler first. So we need to ahead of time compile the Graal compiler to be able to stuff it into a JVM that's not going to spend compiling the compiler forever, all the time. And Graal will stay in there because C2 cannot evolve. So we will have 3 compilers in the JVM in the future for several years to come. Well, of course, I would be that they would replace C1 and C2 with a symbolic JRockit style JIT, of course. But you have seen the arguments. Graal can live concurrently and evolve until we can ahead of time compile Graal into a JIT with the same performance as a JRockit JIT. And we of course have to assume that Graal doesn't fall into the ocean of nodes. So I hope you found this interesting. Thank you very much. Questions?